Hello everyone. I welcome you all to this new video. In today's session, I will be showing you how you can build linear regression models using Python libraries such as Statsmodel and Scikit-learn. I'm gonna start off by importing various libraries. Pandas SPD, NumPy SNP, matplotlib.pyplot as PLT. Additionally, I'm gonna be importing statsmodels.api as SM. That's the library that would aid us in building linear regression models. I have all my data in solubility underscore LR Excel file. So I am gonna be loading this data into our notebook using pandas. Let's go ahead and look at first 5 data points. So this is the data set that I have, which has the name of the organic compounds, their molecular weights, and log of solubilities. You can also call our describe method on the data frame in order to see some more useful statistics. So we have count, mean of the data, standard deviation, and so on. We will not use any of the information here just yet, but it's always a good practice to use it. We have a total count of 1144. That means we have 1144 data points containing their names, molecular weight, and log of the solubility. Now let's dig deep into the problem. So in here we will create a linear regression model which would predict solubilities based on molecular weight of the compounds. I'm gonna close this window over here. Now the big question is, why do we even need to predict the solubilities? Predicting the solubilities of organic compounds is important in various fields and industries for several reasons. In pharmaceutical research as well as agrochemical and pesticide industry, it is crucial to understand the solubility of potential drug candidates or organochemicals, where on one side poor solubility can lead to low bioavailability, limiting the effectiveness of the drug. On the other side, it influences the formulation of pesticides, herbicides, and fertilizers, affecting their effectiveness. Predicting the solubility of organic compounds is essential in environmental studies, especially when assessing the fate and transport of pollutants. It's also important in material sciences, and solubility predictions are valuable in designing new materials, including polymers and organic inorganic hybrid materials. Last but not the least, in the food and flavor industry, predicting the solubility of organic compounds is important for formulating products with desired taste and texture. It helps in selecting suitable ingredients and designing manufacturing processes. Okay, we saw that solubilities are important, but now the next question is, why do we need to predict the solubilities with molecular weights of the compounds? I'm gonna come back to these questions in a bit. Now let's go ahead and define our variables. Since we are trying to predict log of solubilities, so that would be our dependent variable or target. So let me store this in a variable called y. Now molecular weight is a descriptor that makes it an independent variable, and I'm gonna be storing it in a variable called x1. Next, before we go ahead and build our regression model, let's just go ahead and visualize a scatter plot between these two variables and see if there is any relationship between them. I'm gonna be using matplotlib for this, and I'm calling a scatter method on PLT, and it will take in variables as x1 and y. Let's just run this. Let me just go ahead and label the x and y axis as well. As you can see here, on x-axis we have molecular weights of the compounds, and on y-axis we have log of the solubilities. As you can see, there is a negative relationship between solubility and molecular weight. With increase in molecular weight, we saw a decrease in the solubilities of organic compounds. Since we are dealing with organic compounds here, you can think of it as with increase in hydrocarbon chain, the molecular weight would increase. That would increase the lipophilicity of these compounds, which would lead to decrease in solubilities in water. That is the reason we wanna use molecular weight as our descriptor. Well, how true that statement is, that we will know when we will build our linear regression model. Now let's just go ahead and build our first regression model using stats model. The first step towards this process is creating a variable called x. Now if we look at our regression equation, we have x1 but no explicit x0, and we just have b0 which represents the intercept, but that can be represented by b0 times 1. So if there was another constant x0, that could always be 1. For practical purposes, we need to incorporate this into the equation, and that's what we are gonna do here. Use add underscore constant method, which takes in argument as x1, and it will be stored in a variable called x. Let's run this and see what our x looks like. Now as you can see here, with the molecular weight we have a constant and the value of each of these is 1. The next line of code would set up an OLS regression model where y is our dependent variable and x is our independent variable along with the added constant. SM.OLS would be creating an OLS regression model object, and we are gonna be calling a fit method on it which fits the OLS model to the data. It would estimate the coefficients of the regression equation, and I am gonna be storing this in a variable called results. So let's run this, and we can print the results out in the form of a table using summary method. So let's do that. So as you can see here, we have got the results in the form of a table. Now there is a lot of information over here, but I am just gonna be focusing on some important points. Let's first start with our coefficients. This is the constant or intercept for our regression line, and its value is minus 0.3936. That means B0 is minus 0.3936. Below this line is another coefficient with a value of minus 0.0130. That would be our B1, and these are the only two numbers which we need to define our regression equation. Therefore, log of solubilities would be equal to minus 0.3936 minus 0.0130 times molecular weight. So this is how we obtain the regression equation. Next, very important statistics that we need to discuss is R square. Just a quick recap about R square. It's a value which ranges from 0 to 1. 0 means the regression line explains none of the variability of the data, whereas R square equal to 1 would mean the model explains the entire variability of the data. Now if you ask what is a good R square, well, there is no rule of thumb. It depends on the topic and complexity of the problem, but generally R square values closer to 1 are desired. In our case, R square is 0.406. That means molecular weight explains only around 41% of the variability of the solubility for our sample. Since this value is too far away from 1, I would say we are missing some important information. Other features could play an important role in accurately predicting the solubility of organic compounds, such as number of heteroatoms, hydrogen bond donors or acceptors, etc. The p-values here are 0, so that means molecular weight is a relevant feature. Nevertheless, let's go ahead and build a regression line. For that, I am gonna be writing our regression equation here, which is y hat equal to our intercept, which is this constant over here, minus 0.3936, and then minus our coefficient for molecular weight, which is minus 0.0130 times molecular weight, which is our independent variable x1. So this is our regression equation. Now we can use this equation for predicting solubilities with the help of molecular weight. For example, if we want to predict solubility of a compound having molecular weight of, let's say, 500, we can replace x1 with 500 and run this, and y hat would be our predicted solubility for this particular molecule. For drawing regression line, I'm just gonna replace it with x1. In that way, it would provide me the solubilities of all the 1144 compounds based on this linear regression equation. So let's just keep it as x1, and let me just go ahead and show you the output. So you can see here that we have 1144 points, and each of these represents the predicted solubilities of our molecules. Now let me just go up there and copy the code for the scatter plot here, and I'm gonna be pasting it here. Let's run this. Now this is the same scatter plot that we visualized above. Now let me just copy this equation over here. Now within this figure, let me plot another plot here using plot.scatter, and I am giving arguments as x1 and y hat, and I'm gonna be changing the color to green. Let me just run this and show you the output. So as you can see here, this is the scatter plot between our x1, which is molecular weight, and our predicted solubilities, and it's kind of a straight line because that y hat we have got from our regression line. Now in order to convert this scatter plot into a line, all I have to do is replace this scatter with plot so that we have a line. Now you can see here we have the scatter plot and the regression line in the same figure. Next, I want to show you how you can use scikit-learn for building regression models. Scikit-learn is a machine learning package for Python. It is built on NumPy, SciPy, and Matplotlib libraries. There are many advantages of using sklearn. It has a user-friendly interface. Scikit-learn provides a simple and consistent interface for various machine learning tasks. It has extensive documentation. In fact, scikit-learn has comprehensive and well-maintained documentation. This documentation includes detailed explanations of algorithms, examples, and practical guidelines, making it a valuable resource for users to understand and implement machine learning techniques. It has a wide range of algorithms. Scikit-learn provides a vast array of machine learning algorithms for tasks such as classification, regression, clustering, dimensionality reduction, and more. This allows users to experiment with different approaches and choose the most suitable algorithm for their specific problem. While scikit-learn is primarily designed for small to medium-sized data sets, it provides a foundation for users to transition to more scalable solutions. And last but not the least, it is one of the fastest and highly efficient library for building machine learning models. Now, in order to build a linear regression model using scikit-learn, first we have to do is import a linear regression class from scikit-learn.linear_model. Once we have imported the linear regression class, I am gonna be creating an instance of this class. We have stored this in a variable called LR. Next, all we need to do is fit the regression using lr.fit, which takes in argument as x1, which is our feature, and y, which is our target. So let's run this. Now you can see we have got an error which is expected 2D array and got 1D array instead. This is because our inputs are 1D objects, so we must reshape our inputs into 2D metrics, which we can do with the help of reshape method. So up here I'm just gonna first show you the shape of x1. So as you can see here, but this is one-dimensional array, we need to reshape it into 2D metrics. So what I'm gonna do here is I'm gonna be storing it in a variable called x, and I'm gonna call the values method, and I'm gonna reshape it into 1144, which is the size of our data set by 1. So in this way, we are just changing the dimensionality from 1D object to a 2D object. Let's again see the shape of our x. So now you can see we have converted into a two-dimensional object. Now let's just input here instead of x1 and run it again. So now we have successfully fitted our linear regression model. Now in order to see the results, first I wanna see my R squares. For that I need to call a score function with variables x and y. So our R square is 0.406, which is similar to the one we calculated using stats model. And if you wanna see our coefficients or b1, what we're gonna do here is use lr.coff underscore method, which would print out the b1 for our regression model. Now again, let's print out the intercept using intercept underscore. So this is our intercept. Now let's say you want to predict the solubility using this model. All you need to do is call a predict method, and you have to input the molecular weight as a two-dimensional object. So let's say you want to predict for compound having molecular weight of 500. So let's just put it in a two-dimensional array and run this. So this is our output here. So this was all about linear regression. In the next video, I will be talking about how to build multiple linear regression models using Python. And I'm gonna be taking the same data set here, but with more features. So in case you have any questions, you can let me know in the comment section and I will be happy to help. Stay tuned for more videos. Thank you for watching.